This is the 9.5 and 9.6 podcast on kinetic energy and the work energy theorem. To start off, kinetic energy. The kinetic energy of a moving object is equal to the work required to bring it to its speed from rest, or the work the object can do while being brought to rest. Now, here's the equation for kinetic energy. It depends on two things: mass of the object that's moving and the speed, and more specifically the square of the speed. And here's what the equation looks like. Kinetic energy is equal to 1/2 the mass times the speed squared. And this is how we would write it here. We might use velocity instead of speed when we're trying to express it. So when you throw a ball, we said you do work on it. You apply a force over a distance as you throw it. And you can see you do work on the ball, and which is force times distance, and then you cause it to move, which is 1/2 mv squared. So when it's moving, it has kinetic energy. So here's another important thing to remember: that when you square the speed, the kinetic energy is squared. So if you double the speed, then you're quadrupling the kinetic energy. So that means, first, for work reasons, it means you have to do 4 times the work to double the speed, and an object that's moving twice as fast takes 4 times as much work to stop. And we're going to see that later on when we're talking in terms of a car. So how are work and kinetic energy related to each other? The kinetic energy is equal to 1/2 the mass times the velocity squared. Now here's the work energy theorem. What it's saying is that when we do work, energy will change. That means we can do work on one object and change its amount of energy by increasing it, or an object with energy can do work and therefore it's going to lose some energy. So in order to increase the energy of an object, we have to do work on it. A good simple explanation is if you want to make something move faster, you have to push it. You have to apply a force to it. And also, if you want to stop an object, you're also going to need to do work on it to bring it to rest. So this change of kinetic energy, the amount of it, is equal to the amount of work that you do on the object. And the work energy theorem describes this. So let's use the symbol delta, which we know means change in. So we're going to say work is equal to the change in kinetic energy. So that means the work on the object will change the kinetic energy, and in this case, the work that we do will be the force that you apply on the object. So let's look at some situations where no net work is done on an object. If you push something along the floor and it doesn't slide, you're not doing any work on it. And if there's no friction at all, and you push if you push the object on a slippery floor and there's no friction at all, the work of your push times the distance of push will appear as the kinetic energy of the box. So when we're talking about friction here, we have to worry about the net force of the push, which is going to be your push minus the frictional force, and apply that along the distance to give the gain in kinetic energy. So it's not just your push, you also have to take into account the frictions working against you. Therefore, we're going to use the net force on the box. And if the box is moving at a constant speed, then you're not going to have a net force on the box. The force you're pushing and friction are going to balance out and equal 0. So there's going to be no change in the velocity, therefore no change in kinetic energy, and therefore you're not doing any work on the box. Now we've talked in terms of making something move. Let's talk in terms of making something stop or slow down. So the more energy something has, the more kinetic energy it has, the more work you're going to have to do to stop it. This makes sense. Something moving faster is going to take more work to slow it down than something moving slowly. And if you so we can see that energy is transferred into the floor when a bicycle stops, because it creates friction. And if you look at the infrared camera, you can actually see the skid mark right here, which is where the floor got worn from the bike skidding along the floor. And you can also see on the bottom of the bicycle that there has been energy transferred into the floor and into the tire as the bicycle stops, because the tire gets hot too. Now this is important in terms of driving, and especially driving around campus. If you move at every time you double your speed, you're then going to have 4 times as much kinetic energy, and that will mean then is you're going to require 4 times as much work to stop. And as in that case, since the frictional force is pretty much the same for every car, it's going to take you 4 times as much distance to stop. Because you have to remember that the kinetic energy is equal to the speed squared. So if you double your speed, you're quadrupling your kinetic energy, which means you're going to have to quadruple your stopping distance. So let's look at some typical stopping distances. This is 45 kilometers per hour, and 45 kilometers per hour is roughly 27 miles per hour, which is not, it's over the school speed limit, but cars do travel at 27 miles per hour on our driveway. You're going to see it takes you it's a 10 meter skid. Remember, that 10 meters is about 33 feet, which is a pretty good distance. That's that's, I don't know, 30 feet. That's pretty far. Now let's double that speed up to 90 kilometers per hour, which is roughly 55 miles per hour, and suddenly you have a 40 meter skid, which is almost half a football field. And if you double that again to 180 kilometers per hour, which is 110 miles per hour, you're going to have nearly a 160 meter skid, which is a quarter of a mile is 400 meters. So I mean that's a very large distance to skid. Kinetic energy we can often see as other forms of energy. It isn't just something moving from point A to point B. In molecules, there's motion, or in the molecule, in that sense, is heat. We know that sound is molecules vibrating in waves, and light is all about the motion of electrons within atoms. And we know that electrons in motion can make electrical currents. So let's look at some examples here. A friend says that if you do 100 joules of work on a moving cart, the cart will gain 100 joules of Ke. Another friend says this depends on whether or not there's friction. What is your opinion of these statements? Well, I'm going to say they're sort of both right. If you do 100 joules of work on the car, it might mean one of two things. It might mean that you're putting 100 joules in, and then you have to take care of the count for the friction, but it might also be the net work done on the cart, including the friction. So the Ke all depends on how much network you do on the cart. When the brakes of a car are locked, the car skids to a stop. How much further will the car skid if it's moving 3 times as fast? Well, if we triple the speed, we're going to have to do 3 squared times the distance. So it should be 9 times as much kinetic energy, which means 9 times the stopping distance. That's pretty far. So once again, what does the work energy theorem state? It talks about how the amount of work done is related to the amount of kinetic energy an object has to start to get it to move or to stop it from moving.